right, so we are doing 20.1 properties of dilation. So I can dilate a figure around a center of dilation and use an algebraic expression to represent the dilation. So a dilation is a transformation that enlarges or reduces a figure by a common scale factor. So the most common thing that dilates that we know of is our pupils, right? We even say they've dilated. So dilation is both, though, not just an enlargement, it's also a reduction. So a center of dilation is just like the center of rotation. It's a point about which a figure is dilated. Majority of the time we just use the origin 0, 0. So a scale factor is the ratio used to enlarge or reduce a similar figure. So if we don't use the same factor, things will get messed up, right? If I scale the sides differently than the bottom, then it's going to not be a similar figure anymore. Also, if you think about your pupils, and if we changed how we dilated it, if it changed, your pupil would actually change shape. So that's why we don't want that. So an enlargement is an increase in size of all the dimensions with the same proportion, and a reduction is a decrease in size of all the dimensions in the same proportion. So it just means that they enlarge all by the same and they reduce all by the same. All right. Lost my pen. There it is. All right, so we have an art supply store sells several sizes of drawing triangles, so they use them to draw. All are dilations of a single basic triangle. So they have their starting point, and then they just either make it bigger or smaller, same triangle, just they take starting point. That's their single basic triangle. So the basic triangle and one of its dilations are shown on the grid. Find the scale factor of the dilation. So because everything has to change by the same amount, that means the side lengths also change by the same amount. That's what a dilation does. So if I reduce everything and cut it in half, the side lengths have to cut in half. If I multiply and make everything bigger by 3, the sides all have to change by 3 as well. So we need to find how much I change this by. So what we're going to do is look at the side lengths that I can actually find. So we're going to look at AC, and it is 2, right, segment. And then if I look at like CB, it is also 1, or it's 3. Sorry, not also, 3. I'm not going to use AB because I can't count that. And as long as these two change by the same amount, so has AB, okay? So then if I look at A prime, C prime segment, and I count 1, 2, 3, 4. And then I'm going to look at C prime, B prime, and I count 1, 2, 3, 4, 5, 6. So remember, it talked about how it was a ratio and everything needed to change by the same amount. So the ratio is always going to be the image over the pre-image. So in our case, we would do 4 over 2, and our other one's 6 over 3. And if we look, those are actually equal. They're proportionate. They've both been enlarged by the same amount, and they've both been enlarged to 2. So our scale factor is 2. It's been doubled in size. Okay. So for this one, the second one, it's a rectangle, so it's really nice as we can actually check all 4, right? So we would check DE against D prime, E prime, and then maybe EF against EF prime, and so on. I'm just going to write them down. What I want you to do is I want you to check these and see if you can get the scale factor. So maybe a good place to pause, write down your segments, find the ratio, and see if you get the same ratio. Okay, so if I check D, 1, 2, 3, 4, 5, 6. The nice thing is, so is this one. And then 1, 2, 3, 4, right? 1, 2, 3, 4, just want to double check. So this one and this one the same, which is really nice. Oh, not that way. Sorry, those go here. Here we go. Then I'm going to check my prime. That's the smaller one. So now DE is 1, 2, 3. and that makes FG the same, and then EF is only 2, which makes this one the same. Now remember, we still always do image over pre-image, so all my ratios are 3 over 6, 2 over 4, 3 over 6, and 2 over 4. And if we look at all of these, they're actually all equal to a half. So we would say our scale factor equals a half. Hopefully you didn't say 2. If you said 2, you flipped them. Okay, so for this one we need to, they're going to give us the scale factor, and then we are going to do what it says. Okay, this is also where I'm going to introduce our algebraic expressions. Okay, so this is where we'll do that. So remember, if we enlarge it or reduce it, everything has to be enlarged or reduced by the same thing. So the way we would write this would go x, y goes to, and then we're going to use the scale factor. It's a multiplication, so it's going to look like this. And we have to do both of them by the exact same amount. So I'm going to do it longhand and for both of them to show you. So if I take A, B, and C, so 1, 1, 3, 1, and 1, 3. What it would look like is we would go 3 times 1, 3 times 1, 3 times 3, 3 times 1. Notice the first number is always my scale. 3 times 1, and then 3 times 3. So then A prime is 3, 3. And B prime is now 9, 3. And C prime is now 3, 9. So then we're going to graph that. Okay, so 3, 3, A prime, 9, 3, B prime, and then 3, 9, C prime. And then so just like we were saying, the segments change. If you notice, this is by 2 originally, right? 1, 2. This is now by 6. 1, 2, 3, 4, 5, 6. So even my segments did change. They were 2, 2 times 3 is 6. So they all change by the same amount as well. All right, so when we have a scale factor of a fraction, we actually write the rule the same way. We just write our fraction in. So there's our algebraic expression or our rule. So again, I'm going to write down my points, A, B, C. Interesting enough, they're these. So A is at 3, 3. B is at 9, 3. And this one's at 3, 9. So what it looks like is you're going to times just like you did before, technically, but we know that when we're multiplying by a fraction, it's the same as dividing by that denominator. Remember we did this when we had cones, we just divided by 3. So that's what's really nice. All right. And I mean, technically it becomes, 3 over 3 if I do true multiplication, but that just gets me A prime at 1, 1, right? So if I do true multiplication, 9 over 3, 3 over 3, B prime is now at 3, 1. If I reduce those fractions, and then 3 over 3, 9 over 3, and so C prime is at 1, 3. The only reason I bring that up is in case you have a scale factor like 2 over 3, you will have to times by 2 and then divide by 3, just like we did when we had spheres, and we had a times by 4 and then divide by 3. So just be aware of that. It's like that with the cones and the cylinders. So, I mean spheres. So when we times by the numerator and then divide by the denominator. All right, I'm going to graph this. The nice thing is it's actually right up here, right? It's the same one. So there's A prime, C prime, B prime. There it is. You can also check my segments. 1, 2, 3, 4, 5, 6. Divided by 3. 6 divided by 3 is 2. So I did my math correctly. So you can always check your segments to see if you enlarged it or reduced it by the same amount. So the thing I'll give you a little thing to remember is an enlargement. The scale factor will be greater than 1. And for a reduction, the scale factor will be less than 1. All right, so here's your independent practice. Here's your scale factor. Here's your original. I want you to write the algebraic expression. I want you to list your points. I put A. I want you to list your points. So I, H, G, F. And then I think it would be good practice to apply your rule like I did in the video, and then tell me what I prime, H prime, G prime, and F prime are. All right, so apply the rule, and then tell me what they are. You do need to graph them though too, okay? So lots of setup there. And until next time.